Section 2.5, implicit differentiation. One of my favorite topics to teach. I enjoy it, probably just because of the name. Say it a lot. Implicit differentiation. Doesn't that just roll off the tongue? So our goal today, we're going to be able to find the derivative of a relation that's not necessarily a function. So that's going to be kind of something different that we have not seen so far. So far, if you think about all of our functions, all of our relations that we've found the derivative of, they've all been functions, all been labeled as f of x or g of x, and we found f prime or g prime, so on and so forth. Today, we're going to be able to find the derivative of things that are not functional. So some things that would not be functional would be your sideways parabolas, would be circles, ellipses, hyperbolas. So all of those would be non-functional, and we can also find the derivative of them. So we use implicit differentiation when something is not necessarily explicitly stated. Up to this point, again, everything has been explicitly placed in y equals form. Now, we don't necessarily have to have it in y equals form to be able to find the derivative of it. Notice, implicitly, we can say that x plus y equals 5. Well, explicitly, that would be y equals negative x plus 5. Going to our circle, x squared plus y squared equals 4, that would be an implicit statement. Whereas y equals plus or minus the square root of 4 minus x squared, a little uglier looking, but that's the explicit form of what y equals for a circle. So now, as I said before, we can find the derivative of things that are non-functional. What are we going to do and how are we going to do that? Well, we're going to find the derivative of each side of an equation with respect to x. Whenever we take the derivative of y, though, we're going to put dy dx with it. So we've done, and most of our notation has been f prime of x. But we've talked about that also means dy dx. And that's just another notation to represent the derivative of y with respect to x. Once we have the derivative, whenever we take the derivative of y with respect to x, we're going to solve for that dy dx. We may need to collect some dy dx's, and we may have to factor as well as we get into these problems. So let's go ahead and start. We have lots of examples today, so you're going to probably want to put this on, I don't know, 2 times the speed or 3 times the speed to be able to get through it in a normal time. But we're going to do it, and we're going to sit through here. So x squared plus y squared equals 4. To be able to find the derivative, we're going to take the derivative just like we normally would. Derivative of x squared is 2x. Derivative of y squared. Remember, we're taking the derivative with respect to x. So the derivative of y, 2y of y squared is 2y. Whenever we take the derivative of y, we're going to put dy dx with it. So that means we took the derivative of y with respect to x. The question you probably are saying is, well, why didn't we do that with the 2x? And we do really do it. When we take the derivative of x squared, we say the derivative of x squared is 2x, and that's a dx dx. Well, what do we know about dx dx? So it's the rate of change of x with respect to the rate of change of x. So that's going to go ahead and be a ratio of 1. So we end up with just 2x plus 2y dy dx. Derivative of 4 is going to be 0. Be very, very careful. Derivative of any constant is going to be 0. A lot of people like to bring this 4 down because they think they took the derivative of one side and they're done. But it's not. Derivative of 4 is going to give us 0 as well. So here we can go ahead and eliminate those dx dx's. And we're going to go ahead and solve for dy dx. So dy dx is going to equal, subtract your 2x, and divide by 2y. Simplifying that, we get a negative x over y. And as you think about it, x squared plus y squared equals 4. That's our circle. We could put any radius that we wanted over here. The derivative of any radius is going to be 0. So the derivative of any circle is going to be negative x over y. Well, what does that tell us? If you think about this circle here, at any point on this graph, on this circle, we can find the slope. And the slope is going to be the negative x value over the y value. And we're going to see that we're going to have multiple places We can go around this infinitely, but we're going to see that we're going to have two places on the circle where we have parallel lines for the tangent lines. Notice these two parallel, kind of look in parallel, but these 2 points here are going to be parallel as well. So it's going to be something that we're going to see as we get into this implicit differentiation idea and concepts. Derivative of xy plus 3x plus equals 5. So this one I show you because we have a multiplication there. We have a product rule. Yes, we can do implicit differentiation with the product rule. And you guessed it, we can also throw the quotient rule in there. So product rule, we have x dy dx, because we took the derivative of y. So we're going to add y, our second derivative of the first, which is 1. To that we're going to add derivative of 3x, which is 3, and derivative of 5 is 0. So notice, be careful, we put a dy dx with this one, but not with this one. Well, why is that? We put the dy dx here because we took the derivative of a y. Here, this tells us 2 d1. So it doesn't ask us to take the derivative of a y here, it takes the derivative of an x. And derivative of x is 1 dx dx if you want, or just 1. Go ahead and solve for dy dx. We're going to subtract the 3, subtract y, and then divide by x. And that's going to be our derivative. We can get ugly, we can get nasty, and we can get very nasty. So this example, probably one of the nastier ones we're going to see. We have y to the fourth derivative. We have 4y to the third dy dx. Derivative of x times y squared. So we're going to add x, derivative of y squared is 2y dy dx plus y squared times 1. And then we're going to subtract, and I'm going to put in brackets because we have to multiply that negative to everything. We have to make sure that we take the negative of this derivative. So we have x dy dx and plus y times 1. And that's going to equal derivative of 3x, which is 3. Notice I have multiple dy dx's in here. So I'm going to go ahead and pull my dy dx's to the left side and everything else to the right. Also recall we're going to multiply that negative through, so this is actually a negative y and a negative x dy dx. So I have 4y to the third dy dx. To that I'm going to add 2xy dy dx. All I did was rewrite this so it's in kind of a nicer looking form. We put our constant first, our x's, then our y's, and dy dx. Minus, I'm going to pull this x dy dx out of here. And I'm going to equals my 3. I'm going to subtract my y squared. And I'm going to add a y. Remember, we multiply that negative through, so it's a negative y. Adding it over, we get plus y. Now we have all of our dy dx's on the left side. I want to get down to 1 dy dx. So I can factor out a dy dx on that right side. So I have 4y to the third, my 2xy, and my negative x. And that's going to equal a 3 minus y squared plus y. Now to get dy dx by itself, I can go ahead and divide by my 4y to the third plus 2xy minus x. And that, my friends, is going to be what my derivative is, dy dx. So dy dx is 3 minus y squared plus y, that is a y, over 4y to the third plus 2xy minus x. Oh, look, derivatives of trig functions. Yes, yes, yes. So derivative sine of x plus y, angle of x plus y, equals x. So can we find the derivative of this? And of course we can. We have a chain rule there, don't we? So derivative of sine is cosine. The angle is going to stay the same. And we're going to multiply by the derivative of the angle. So 1 plus dy dx. And that's going to equal the derivative of x, which is 1. Now I'm going to get dy dx by itself. Notice dy dx is in this quantity being multiplied by this trig function. So to peel things away, I'm going to divide by the cosine of x plus y to both sides. And I end up with 1 plus dy dx. is going to equal 1 over the cosine of x plus y. I can subtract my 1 to get dy dx by itself. So I get 1 over the cosine of x plus y minus 1. If you want, you can find a common denominator. That would be cosine of x plus y. So you'd have 1 minus the cosine of x plus y over the cosine of x plus y. If you want, I can write that out as well. And that's only if you needed it for a common denominator, if maybe it was a multiple choice question. And there you go. I've got more. Here we have 2 tangents of xy equals -1. Can we find the derivative of this? And of course we can. So we have another trig function. We have 2 secant squareds of xy times the derivative of xy. We have a product rule, derivative of the angle measure. So we have x dy dx plus y. And that equals derivative of -1 is 0. So we can go ahead then and solve for dy dx. Well, we're going to go ahead and divide by 2. Hey, 0 divided by 2, that's 0. We divide by the secant squared of xy. 0 divided by that. Hey, that's still 0. So really I get x dy dx plus y is going to equal 0. Solve for dy dx. I can subtract y and divide by x. So dy dx is going to equal a -y over x. Another one, here we have a chain rule where we have the quantity to an exponent. So we're going to have 2 sines of x plus cosines of y to the first. Derivative of the sine of x is cosine of x. Derivative of cosine of y is negative sine of y. Derivative of y, dy dx. That equals the derivative of 2, which is 0. Now I can go ahead and again get dy dx by itself. I'm going to divide by 2. Look, still 0. Divide by the sine of x plus cosine of y, 0. So I have the cosine of x minus the sine of y, dy dx, is going to equal 0. So I can subtract my cosine, divide by sine, and dy dx is going to equal the cosine of x over the sine of y. Remember, this was a negative cosine coming over. Divide by a negative sine gives us a positive cosine of x over the sine of y. So what really can we do with this, and what's it going to ask us to do? Well, it's going to ask us to find the derivative and evaluate at a given point. We could also evaluate and find the equation of tangent lines if we wanted. So this one's just asking us to derive it and evaluate. So the first thing we're going to do is find the derivative. We have a chain rule, 2x plus y to the first. Derivative of x plus y is 1 plus dy dx. And that equals the derivative of 4, which is 0. So I'm going to divide by my 2, divide by x plus y. So 1 plus dy dx is going to equal 0. Dy dx equals -1. So actually there's nothing to plug in. What I would do though, if I had x's and y's, we would plug in my x equals 1 and my y equals 1. And that would give us our derivative. So maybe if this was a 4x, how would that change it? Well, we could change that. 0 then would be a 4. So then we would have 4 over my 2 times x plus y. So I divided that over. And I subtract 1. So I'd have 4 over 2 times x plus y minus 1. If I want the point 2 or 1, 1, the way we can write that, remember, if we were just plugging the x value, maybe we would have f prime of 1 or f prime of whatever value it is. Well, in this case, since we are in 2 variables, what they like to do is to put this kind of subscripted. So dy dx of the point 1, 1 kind of gives you an idea of what they're plugging in. So we have 1 plus 1, which is 2, then minus 1. So we get 4 over 4, which is 1, minus 1, or 0. And that would be the slope at that point with that equation. So that's just another example of where we would see some implicit differentiation and the way they could test you on that implicit differentiation. So good luck, enjoy, and have a good time with it.